the name of the Almighty, the Compassionate, the Merciful. Today we are going to speak about one important subject, which is the inverse of a function. When does a function has an inverse? It's equally actually important as the composite function as well. We meet inverse functions, like for example, we know that the logarithmic function and the exponential one are inverse to one another. So actually we have to know what are the features of inverse functions before we proceed to differentiate such functions, etc. In this lesson we are going to follow the following line of the course. First of all, we have to speak about one-to-one functions, and then what are the steps to obtain an inverse function. Later, how can we draw by simple ways inverse functions, and then we speak of the logarithmic function as an important inverse function, and then later the inverse trigonometric functions as well as the inverse of hyperbolic functions. Now, what's the meaning of an inverse operation? When you say, for example, y is equal to s squared, this is a function. What's the meaning of this function? In other words, what do you exactly do when you specify, for example, I want the square of a number? In fact, suppose, for example, you have a number like 7. When you say you want the square of 7, you mean, in fact, you want to calculate its square, which is 49. On the calculator, all you have to do is to touch 7, enter 7, and then you push the button x squared to get 49. This operation is one way. 7 is equal to 40. 7 goes to 49. This lies in the domain of the function, and this in its range. The inverse operation is exactly the converse of this operation, in the sense that you ask the opposite question. Instead of saying what is the square of 7 to get 49, you say what is the number 1 squares gets 49. What is the number when 1 squares gets 49? In fact, you can square 7 and minus 7 both give 49, but you choose only 7. Why you choose 7 and not minus 7? Because in fact here in this operation, which is y is equal to x square, you have this branch here. In other words, 7 gives 49. If you wish to obtain the opposite, you wish to get the opposite answer, or the other answer, or the other alternative, or the other choice, which from 49 you get minus 7, you have to consider a different function of this function. For example, you can say that this is still y is equal to x squared for those values of x less than or equal to 0. So actually its inverse operation becomes like that. If you here have 49, you get what? You get minus 7. So see, if you have here 7, you get 49. Still, if you have 49, you get minus 7. So in fact, these two operations are inverse to one another. So the problem is now, is any function has an inverse? Not necessarily true. You may not have an inverse of a function. Here you have to notice something, that the square root of 49 is equal to 7. When you say square root of 49, you mean 7. It's not minus 7, because actually this is one common mistake for students. When they write square root of 9, they write it for plus or minus 3. No, it's equal to 3. And same thing when you write, for example, x squared. It's not equal to x, and it's neither equal to plus or minus x. In fact, it's equal to mod x. So here when you say the square root of 49, you mean exactly 7 on the graph here, if you consider this function. As to this one, the function here is not, the square root of 49 is not equal to minus 7. On the contrary, it's minus the square root of x, which in fact is the opposite function, or the inverse function to this function. So the problem now, what are the functions, or what property should the function have in order to have an inverse? Here is exactly what we have, that you have the function f mapping 7 into 49, whereas 49 goes into 7. In other words, x squared brings x into 49, and whereas square root of x brings 49 into 7. So in fact, from what we see here, the domain of the function f is in fact the range of the function f minus 1, which goes from here to here. As to the range of the function f, in fact, it's equal to the domain, to the inverse function f minus 1. So exactly the opposite, the inverse function does exactly the opposite operation. In fact, if you want to square 7, you get 49. And if you want to get the square root of 49 it's equal to 7. In fact, you can do both operations. In other words, you can get the square root of 7 square. If you want the square root of 7 square, you got 7. What have you done here? You have moved from here to here, and then you go back to the same point where you started. And as a matter of fact, same thing when you move from 49 to 7, the square root of 49, and then you square it, you get what? You get also 49. You move here, and then you go back to this point. So actually, you have to end up with the same point where you started, if it is meant to be really an inverse function. Now, the problem is the following: has any function has an inverse, or does all functions possess inverses? Not true. For example, a function like y is equal to x squared. Here, the functions scan the whole domain of f. When you say y is equal to square, you have two choices. Either x1 is equal to square root of y, or x2 is equal to minus the square root of y. So what you notice here is that 7 gives 49 as well as minus 7, and this is actually permitted. It's permitted that the function, two values of x give one value of y. This is permitted in functions. But what is not permitted, we said this in the third lesson, what is not permitted, that when one value of y gives two values of x if it should give an inverse. In other words, x cannot, what is meant by function, a function maps one x into one y. And in fact, this applies to x1, x2. One x gives one y, one x gives one y. But one x does not give two y's. So actually, this is not the case here. So this is a function. But the problem is that when you have one y here, you get two different values of x. So this 49 gives either 7 or minus 7. And this is actually is not permitted. In order that a function has an inverse, if you draw a horizontal line parallel to the x-axis, it must cut the graph in only one point, so that one value of y gives only one value of x in order that the function has an inverse. We call such functions injective ones. Injective functions are those functions where one value of x give one of y, and this is goes without saying, but also one value of y must yield one value of x. So in fact, this is not an injective function. Why? Because one value of y, if you draw here a horizontal line, it gives three values of x. So actually, this function has no inverse. In fact, in order to, instead of just drawing lines and say, and apply the fact that you try a value of y and see the corresponding values of x and see whether there are many or there are only one, unique one, all you have to do is that you consider, for example, a function to be monotonically increasing. If the function increases all the time, surely one value of y give one value of x. So actually, this is a sufficient condition. If the function is monotonically increasing only or monotonically decreasing, then it must have an inverse function. Of course, such a sufficient condition, but it is also necessary if the function is continuous. And usually, most phenomena that you have in engineering are continuous, and therefore, for functions which are increasing or decreasing, they possess an inverse. So here it is. Now, this one, it's decreasing here and then increasing again. And actually, one value of y gives two values of x. So this one is not, this function is not injective, and this function has no inverse. Whereas here to the second one to the left here, this is an increasing function of the time, and therefore it's an injective function in which one value of y gives one value of x. And you realize here that if you have x, the function tells you that y is equal to x cubed. And what is the opposite function? What is the inverse function? The inverse function is that if y is equal to x, then x is equal to x power third or y power third. In other words, when y is equal to x cubed, x is equal to the cubic root of y. So the inverse function to this function is the cubic root of y. And actually, as you see it here, the domain and range of this function is R. Same thing applied to the domain and range of the inverse function to this function. Now, here again, we set the fact that since f up is is a rule of correspondence that assigns to every x in the domain of f one unique y in the range of f. Therefore, f minus 1 must do the opposite thing, or the opposite job, in that it maps one value of y in the range of f into one value x into the domain of f. So in other words, this applies always. The domain of f minus 1 must be equal to the range of f, whereas the range of f minus 1 is equal to the domain of f. In fact, there is one thing which one should say, that, for example, suppose you have y is equal to x squared, and we wish to obtain the inverse of this function. Here, suppose y is equal to minus 1. One can take in the range of f one value is equal to minus 1 to get the value of x? Of course not, because if you set y is equal to minus 1, you get x squared. We cannot have x squared real is equal to minus 1. Therefore, in fact, the values of x in the domain of f minus 1 must be restricted to the range of the function f in order to do the inverse operation. In other words, since f works from the domain, its domain, to its codomain, suppose this is R, for example, then f minus 1, if it is not R like this one, for example, it maps all the values. Suppose I take to make it general, the codomain of f. Then f minus 1 should work to its domain, to the range of f, because I cannot take values apart from the range of f to substitute in the rule of the inverse function into the domain of the into the range of the inverse function, or in equal terms the domain of the function into f minus into the domain of f. So we see actually here that we must have as those must be equal. In other words, we must have as range of f equal to its codomain. In other words, the function must be what you call onto function. In other words, we call it in English surjective. In other words, we can restrict the codomain of the function to be equal to the range of the function in order to have an inverse as well. So actually, we have now two situations. The function must be, this is not permitted to have functions of this sort to have inverse. In other words, the function must be first injective, and also must be surjective in order that its codomain must be filled into by the range of f. But of course, this can be done always. So what's really important is the function to be injective. So in actual terms, if the function is both injective and surjective, we call a function is bijective, and this is actually a condition, a one-to-one function, in order the function has an inverse. So you can put it in this way. We say that a function f minus 1 or a function g, for example, has an inverse to a function f if and only if f minus 1 of f of x is equal to x for x lying in the domain of f, and at the same time f minus 1 of y is equal to y for all y lying in the range of f. This is actually the condition in order that f minus 1 be an inverse to a function f. And actually, if this is satisfied if f is bijective. Now, what are the steps to obtain f minus 1? You have two ways of doing it, either by algebra or by drawing. First of all, you make sure that f is 1, 1. This is, for example, if it's monotonic increasing or decreasing, then you know that it has an inverse. It's injective. And then you solve y in terms of x to obtain, in other words, you make x a subject. X is equal to f minus 1y. And this is the inverse operation. This is the inverse function. And then at last, you can replace x by y to get y is equal to f minus 1 to 1. Same thing for the cosine, which shows a region from 0 to pi. This is the region in which we seek to find the inverse function. So actually, this is the inverse function to the cosine function. And again, this is the tangent function. Tangent function, which shows, because it's not, again, injective, so we chose our region from minus pi by 2 to pi by 2. And the inverse of the tangent becomes from its range from minus pi by 2 to pi by 2, while the domain is R. And these are the secant minus 1, cosecant minus 1, cotangent minus 1. Some books, like I did here, write it in this way, but actually you can plot it different way. You can, for example, have it in this form. Why you have it in this form? In order that sec minus 1 x is equal to cosine minus 1 1 over x. Actually, a calculator usually prefer to draw it in this form, so that actually when we come to derivatives, you will find that the derivative is always positive, whether it is x is negative or positive. So actually you can choose this way. The cotan, as a matter of fact, you can always choose in different way, because here the range of the cotan minus 1 is from 0 to pi, whereas the range of the tan minus 1 is from minus pi by 2 to pi by 2. And this is why it is probably more preferable to have this is tan minus 1 minus pi by 2 to pi by 2. And then you can take the cotan minus 1, and this is tan minus 1. You can take it this way from pi by 2 like this, and here reason why people prefer sometimes to take this drawing here, because actually the function, they take it from 0 to pi, the cotan of which this is the inverse, they take it from 0 to pi because this is an injective function. But you can actually, what you can do here is you fill the hole here, and this becomes the inverse of the cotan function. And if you add up both, you get direct the tan minus 1x plus cotan minus 1x is equal to pi by 2 for x positive, and minus pi by 2 for x less than 0. So that, for example, if you have x is equal to minus 1, here becomes, the summation becomes minus pi over 2, because this gives minus pi over 4, and the same thing for cotan minus 1. So actually, you may, this is not the only choice for the sec minus 1 or cosec minus 1 or cotan minus 1. Same thing, these are the inverse functions to the sine the hyperbolic function, whether sine or cosine minus 1 or tangent minus 1. Of course, in any book you would find, for example, that the cosine, since the range starts from 1, so the domain of cosine minus 1 starts from 1 as well. There is something here to be noted. Since the hyperbolic function, since the hyperbolic functions is given in terms of the exponential, so we expect that the inverse hyperbolic function must be given in terms of the inverse of the exponential function. And in fact, if we try to solve this equation here, you multiply by 2, you get e to the power x minus e to the minus power x is equal to 2y. So if you try to solve this equation for x, make x a subject to obtain the inverse function. In other words, if you want to solve this equation, what you can do is that you multiply this equation by e to the power x. So you have something like this, minus 1. And then you try to resolve e to the power x is equal to what? 2y plus or minus square root of 4y squared plus 4 divided by 2. And of course, because this is positive, you cannot admit negative values, so you have y plus square root of y squared plus 1. What is that? In fact, x become then the logarithm of this quantity. In other words, you get the inverse function. So in fact, the inverse function of the inverse function of the sine function, the sine function, the sine hyperbolic inverse can be expressed in terms of a logarithm, since the sine hyperbolic is expressed in the form of exponential function. Suppose, for example, that you wish to calculate the inverse of such function, the logarithm of e to the exponential minus x minus 1. First of all, is this function injective? Yes, because it's increasing all the time, and it looks to be continuous, of course, here. So actually, this function for x greater than 0, this function is monotonically increased, therefore it has an inverse, and this is and they want you to show that this is the inverse function. What you can do, you solve x in terms of y, simply by that. You get e to the y is equal to the e to the square y minus 1, and then you get this, you move this to the right hand side, you solve x in terms of y, you get square root of x equal to, you take the logarithm of both sides, and then finally x is equal to this expression here. In other words, you can replace x by y, and the inverse become y is equal to the square of logarithm e to the x plus 1. Here they ask to prove that 10 minus 1 over x plus 10 minus 1 x is equal to pi by 2 for x greater than 0. All you have to do, you take y is equal to 10 minus 1 x. Therefore, x is equal to 10y. But since 10y is equal to cosine pi by 2 minus y, what you get here is 1 over x is equal to the tan of this expression here. In other words, that pi by 2 minus y is equal to 10 minus 1x. So what you get here finally is that pi by 2 is equal to what? Is equal to y, which is 10 minus 1x, plus 10 minus 1, 1 over x. And actually, this is what you have thought to prove it. So actually, 10 minus 1x plus cosine minus 1x is equal to pi by 2. And sine minus 1x plus also cosine minus 1x is equal to pi by 2. This is one basic theorem. It's not very important in this course, but it applies to many operators. Even in matrices, for example, we'll see that, for example, that AB to the inverse is equal to B inverse multiplied by A inverse. And here, actually, what you do is that they tell you if you want the inverse of a composite function, you may find in terms of the inverse of each, you get the inverse of the second one. To make it the exterior function, and you take you compose with it you compose with f minus 1 as a composite function to obtain f circular j to the minus 1. In other words, suppose f is equal to sine and the j x square. So here f of j of x is equal to sine x square. Now now y is equal to what? Sine x square. So you get x square is equal to y. Sine minus 1y. Since x squared is equal to sine minus y, so the inverse function directly is what? The square root of sine minus 1x. As a matter of fact, you could have done the same thing by calculating g minus 1x and f minus 1x, and then try to compose the composite function the circular f, which is the square root of sine minus 1x. So with this, actually, we have with this ended our lesson, and we spoke of the conditions for the existence of an inverse function. We actually explained two ways for obtaining this inverse function. We said first that the function has to be injective and surjective. To be injective, if it is monotonically increasing, then this is enough. And this is the way usually most people try to do in order to check whether a function has an inverse. And once you check this condition, you can move to obtaining this inverse function. Either you do it by drawing the graph and then rotating, as we've seen, 90 degrees, and then you put a mirror, or you can do it algebraically. And finally, we took some examples, and we later exposed the trigonometric functions and how we choose a certain restricted range because they are not injective functions. And we displayed some graphs of both the trigonometric and hyperbolic functions. And with this, we have come to the end of this lecture, and hopefully it has been fruitful. This lecture, together with the others, all of them are going to be uploaded to the site of MedNetU. This site is the one that is administered by the Consortium Neptunum for distance learning, for online learning or distance learning, in the hope that you have access to all the lessons designed by Neptunum and the professor that they visit Neptunum. With this, we have come to the end of our lecture, and I thank you for your attention, and until we meet, thank you very much. 1x. In fact, you are not, it's not compulsory, you are not obliged to do this step. This is the inverse function, but you usually do the step y because suppose, for example, we have something like this: y is equal to x cube. Then y is equal to x cube. If you have a point A on x, you get a cube. While the opposite function, it maps x into the cubic root of x. So if you have b here, you move till you get b to the power third. So actually this is the inverse operation. A gets a cube while b get cubic root of b. But you realize here that both operations are achieved, are accomplished on the same graph. And we usually like to have the independent variable of f minus 1 to be on the x-axis. And this is why we prefer that instead of writing y is equal to x cube and x equal y to the top power third, which is really the inverse function, you might as well write y is equal to x power third. And with this, you draw another graph, which is actually the converse to this graph. That's it. Suppose you have y is equal to x square. If you have y is equal to x square and x is less than equal to 0. With this graph here, what is the inverse operation? Here, the domain of this function is, we'll do it here. Here, the domain of f is from minus infinity till 0, and the range of f is from 0 to infinity, which is x squared for x less than equal to 0. So what's the inverse? The inverse, as we said before, you do the following operation. You solve x in terms of y, so you get x is equal to square root of y. Of course, you have positive or negative, but since x is negative here, so exclude the negative, the positive sign, to obtain minus square root of y. This is the converse operation. But since you like always to have as variable, independent variable on the x-axis, you might do this, y is equal to minus square root of x. And this is the inverse function to this function. Now here you realize something, that the domain of this function, which is from 0 to infinity, is in fact the domain of f minus 1 is from 0 to infinity, is exactly equal to the range of f, while the range of the function f minus 1, which is from minus infinity to 0, is exactly the domain of f. So the domain of f is equal to the range of f minus 1, while the range of f is equal to the domain of f minus 1. And you realize directly that if you draw both graphs together, you will find, as you see here, that they are in fact symmetric around the line y is equal to x. Why is that? Because here, for example, you have the point minus 7, you get 49. So the point here, minus 7 and 49, lies on the graph of f, while the point here on the other side, you have 49 and minus 7 lying on the graph of f minus 1. So the point P of A and B on the graph of f is the same as correspond to the point P of B and A on the graph of f minus 1, and therefore both must be symmetric around the line y is equal to x. Another example here, you have f of x is equal to x cube. What's the inverse of this function? Directly, f of minus 1 is equal to x power third. And you see here they're overlapping each another. This one here is x to the power third, while the other one here is x cube, and both have domain and range R. So we have to state this fact. This remark is that the symmetry around the line y is equal to x. The reason is that the point P of A, B, like we said, on the graph of f corresponds to the point P of B of A on the graph f minus 1. Now find the inverse function of f is equal to square root of 5x plus 8. Now what we do is that we have to solve x for y. So you have here y is equal to square root of 5x plus 8. So you get 5x plus 8 is equal to y square. So x direct is equal to what? Y square minus 8 divided by 5. So the inverse, you can write it better in this way, x square minus 8. And this is the inverse function. If you want to draw this inverse function, directly you can do it this way. Now here, since this must be greater than 0, so it starts from 8 or 5, and this is the original function. This one here, it goes like this. So in fact, both are symmetric around the line y is equal to x. The point minus 8 over 5 and 0 correspond to the point 0 and minus 8 over 5. While this point here, for example, is equal to what? Is equal to square root of 8. And this point, in fact, here is equal also to square root of 8. So as you see, the points are symmetric with the line y is equal to x. If you wish to check whether this function is the inverse function or not, we can actually check the two operations which we wrote them as follows. F minus 1 of f of x is equal to x for all x lying in the domain of f, while f minus y is equal to y for all y lying in the range of f. These are the two operations which we perform on the function f minus 1. Here are they. So what you have here, what is the inverse function? The inverse function is 1 over 5 y square minus 1. So here actually we have y square y because y is equal to square root of 5x plus 8. So what we have here is in fact what? F minus 1 of what? Of f of x. This is f of x is equal to x for all x lying in what? The domain of f. The domain of f, as we saw here in our graph, it starts from minus 8 over 5. So actually it's from minus 8 over 5 till infinity. While if you take the square root of this expression here, in other words, if you consider f, this is f, square root of what? Of 5 of what? 5x in terms of y. In other words, f of f minus 1y. This is f minus 1y. F minus 1y is 5x plus 8, you remember. So it's f, this is f of f, exactly, f minus 1y is equal to what? It's equal to y for all y lying in the range of f, which is all values of y greater or equal to 0. And therefore, since this is applied, we can say that we checked the inverse function, we find it correct, and therefore this is the inverse function, the order pair xy, the set of order pairs such that y is equal to 1 over 5 x squared minus 8 for all x greater or equal to 0, because this is the domain of what? Of the inverse function. Now, this is the algebraic way of doing it, but there is an easy way of doing it. Suppose you have, for example, this is the inverse function. This is the function which you want to find the inverse. We call this step 1. First you begin to draw the graph of f, and then what we do is that on the same paper you turn it 90 degrees like this. When you turn it like this, you get like you have here, we get here this graph. This is step number 2. And after you have step number 2, you put here a mirror. When you put a mirror, you get what? Graph of f minus y in this way. It starts on the lower side to the right. This is the graph. So in steps from the beginning, you draw the graph of f, and then you rotate it 90 degrees anti-clockwise. And then you put a mirror here to obtain this graph. So in fact, after you have, this is step 2, this becomes now step 2. You put a mirror here to obtain a function like this. So in other words, it becomes like this, etc. So actually, this is the way you do it. Anything you can imagine. Suppose, for example, you have y is equal to x squared. What you do is that first you put it like this, and then you put the mirror, so it's like this, etc. So this is the way of doing it. And in fact, we have here an applet which you can show it to. Suppose this is the exponential function, and we know that the exponential function has a logarithm as an inverse function. So the first thing is what? We rotate it 90 degrees, and then we put a mirror. And this becomes the logarithmic function, which is the inverse function of this function. And you notice that we could have here marked the line, draw the line y is equal to x. Both of them are symmetric with respect to the line y is equal to x. Suppose you have another function. This is, for example, y is equal to x cubed. To obtain the inverse, what we do is that you rotate it 90 degrees. And then you put a mirror. So you obtain this graph. Here it is. This is the inverse function to x cubed. And of course, both of them are symmetric around the line y is equal to x. Finally, suppose you have y is equal to cosine x. from 0 to pi. Of course, cosine x in general has no inverse. Why it has no inverse? Because it's not an injective function. There are some values of y which have different values of x for the same cosine. So we choose a domain from 0 to pi, and this domain here, the cosine has an inverse, and therefore what we do, we rotate it 90 degrees, and then we put an arrow, and that's it. And that's the inverse function. And you see as well here that the same thing applies. They are both symmetric around the line y is equal to x. So one actually of the applications of calculating inverse functions, for example, students usually suffer from, they say that they complain that they know how to obtain the domain of functions, but not to calculate its range. So one actually of the applications of inverse function, you can calculate range of function. For example, if a function of this sort is symmetric around the y-axis, of course it has no inverse. But suppose we consider this function in the positive real axis, and we wish to obtain the range, which is the same range whether it is symmetric or not. I'm sorry, whether it is drawn on R or not. The range is the same. And suppose you need to calculate the range of this function. So what you do, because the range of this function becomes the domain, the domain of the inverse of this function is the range of this function. In other words, if you can obtain the domain of the inverse function, it becomes equal, same thing, to the range of this function. So we seek to calculate the inverse of this function. Here is the function, which we know that its domain is R. Why? Because there is no one single x here which this doesn't function, so the domain is R. But if we take x greater or equal to 0, y, we want to restrict ourselves to this domain just because the function is not injective, but the range is the same. So what we do, we calculate the inverse. We solve x in terms of y to obtain this expression here. And here, since y is positive from here, then 2 minus 8y must be also greater than 0. So in fact, the domain of this inverse function is what? Is all values of y such that 2 minus 8y is greater or equal to 0, which gives y greater than 0. It's not equal to 0 because you divide by 0, by y. And so greater than 0 and less or equal to 1 over 4. This is what? This is the domain of the inverse function. And it is the same thing as the range of f. So in fact, we were able to calculate the range of f by calculating the domain of its inverse function. The logarithmic function is what? Is the inverse function to the exponential function. And this is how we draw it, and we saw it before. These are drawn for different values of a. You have logarithm a of x. Of course, a is not equal to 1. Why? Because we cannot consider a to the power x where a is equal to 1, because this is not an injective function. So we can take any value of a positive, but not a is equal to 1. And therefore, we can trace all values of logarithmic function for different value of the base. When you write ln, you mean logarithm to the base e. And this is the logarithmic function as a matter of fact. And it is what? It is valid only for those values of x greater than 0. Why? Because the exponential function has range y greater than 0. And since the domain of the logarithmic is equal to the range of the exponential function, so it must be confined to the region x greater or equal to 0. Again here, we apply the rule here. F minus 1 of f of x is equal to x. For all x lying in the domain of f, the domain of e to the power x is R. And again here, f of f minus 1 of y must be y equal to y for all y lying in the range of f, and the range of f are all values of x of y greater than 0. So either you write e logarithm y is equal to y, or e logarithm x is equal to x for all x greater than 0. These are the inverse of logarithmic functions. Here, the sign has no inverse, as we said, because you may have the same sign for different values of x. So it's not injective. So we choose a region in which f becomes injective. So for example, we can choose from minus pi by 2 to pi by 2. And this is the inverse of this function. It goes, since here the domain from minus pi by 2 to pi by 2, so the range of the inverse function is from minus pi by 2 to pi by 2, while the domain of the sign minus 1 is from minus 1 to 1, because the range of the sign is from